Our second talk today, we have two speakers, Gil Bauer, Aylin, and Emilia Katz, both from Intel, both located in Israel, where they're both formal verification experts. They're talking about noise reduction in coverage-based formal verification. They both work in Intel Israel's CPU department. Gil Bauer has over 25 years at Intel and leads sign-off methodologies and founded Formal Verification Israel, a conference that runs in Israel once a year. And Emilia holds a PhD from the Technion and develops verification tools and methodologies. Both contribute significantly to advancing formal verification practices and local engineering activities. And just to say, Gil Bauer is also helping us set up a DV club in Israel, close to Tel Aviv. His formal verification conference happens in Haifa, and we're going to set up a DV club in Tel Aviv with his help. So thank you to Gil Bauer for that, as well as speaking today. And we'll hand over now. Noise reduction in coverage-based formal verification, please. Thank you.
Thank you, Mike, for the introduction. So today, Emilia and I will present a work that we developed and implemented at Intel named Noise Reduction in Coverage-Based FV. This is the agenda, and we'll start by motivation and problem statement. The first slide shows how FV becomes mainstream, and the diagram on the right is made by Harry Foster from Siemens, and it shows that FV is adopted more widely as years go by, and that's not a surprise for you. What's important for us is the last bullet. Do you take full responsibility on your FV tasks, or is FV just an add-on to the simulation and other tasks? And what we claim is that for getting full responsibility, you don't have sign-off criteria. Looking on DV, their flow is well established. They have the test bench development, they run simulation and regressions, and eventually sign off by checking code and functional coverage. For FV, we have more or less the same. We write our properties in the environment and then run them, debug, and deal with convergence. And coverage is our vehicle for sign-off. Just to recap on what do we mean by FV coverage. So coverage can be measured on design inputs and outputs and code statements, branches, and expressions. And for formal, we mainly look on these two coverage, stimuli coverage and checker coverage. Stimuli for checking that each cover can be covered and there are no over constraints that limit us from getting there. The checker coverage verifies that each cover item is used by at least one assertion. And coverage is the best method that we have so far for design reliability. Just we need to remind ourselves from time to time that it is not absolute, and even full coverage does not guarantee no bugs, but that's the best we have. Okay, then what's the news? We have commercial tools. One of them will be presented soon, and they create the covers and perform checks very well. But if you have a medium or large size design, you get a high volume of covers, which is good, but it can lead to numerous violations. And then you have to inspect them manually, and that's time consuming and error prone. What we're afraid of is these two issues: premature termination. You worked for 5 days and then your manager says that you need to stop. And the streetlight effect. You think that you worked on 95% of the issues, but you chose to work on the easiest one and not on the complicated ones, which might hide the bug. Bottom line is that we need a robust FV cleanup methodology. And that's our target. And on the next two bullets, we're talking about the stimuli cleanup methodology and then on checker cleanup methodology. We want to clean the 1,000 or even more unreachable covers that the tool provides us. And in the picture below, we show a case, a scenario that is given from the tool with all kinds of unreachable properties. And we have to clean them. And the traditional method is to use pattern matching. If we look on the first one, we see the name case 1, obsolete feature 2. We recognize that obsolete feature is something that we want to waive. So therefore, we waive all violations that have this pattern. And that's good, and it reduces massively the number of violations. But there are two main concerns. One of them is that some cover items have names that are not meaningful because the tool creates them from some internal signals. So it can be temp cov 1 or toggle signal 1, and it's hard to tell by pattern matching whether they are good or whether we should waive them or not. And another issue that we encountered is that sometimes the pattern can hide some real issues. For example, we took a pattern obsolete feature, but there is a cover item named obsolete feature replacement. And that's something that you probably don't want to waive, but using the pattern, you'll waive it. Therefore, we're not happy with the traditional cleaning stimuli failures. Instead, we decided to invert the checking process, not going over the list of failures, but start from the assumptions themselves. So what does it mean? Here we see the results that are given on the top diagram. We see the results that the tool gave us with reachable and unreachable cover items, and we have to clean them as before. What we do is first remove all the assumptions and run the coverage again. Now we're not supposed to see any unreachable because they have no assumptions. If we do see cover items that are unreachable, they're actually dead code and not related to over constraint. Therefore, we waive them, and you'll see in the next diagram they are marked in black. On the second stage, we start adding assumptions that we have high confidence on. Assumptions that come from spec or known restrictions or are checked by the neighboring blocks. So we have high confidence on them. We can apply them and run the coverage again. We will get some unreachable covers, but that's okay. We know the reason. It's because of one of our high confidence assumptions, and therefore we can waive them. So you can see from the first assumption to the second assumption, we have more waived, and eventually, as we progress with getting high confidence on our assumptions, we get less and less unreachable covers. We might get to 0 unreachable covers or a small number that requires more work either to debug the assumptions and make sure that we are having high confidence on them, or that the specific cover item that is unreachable. We'll see in the results that we got to very nice results on our designs. That was the stimuli, and now let's go to the checker. For checker, the tools provide mainly two checks. One of them is the COI, cone of inference, and this is a structural check. It is simple, quick, and give coarse results. And now what's our flow for cleaning it? We first remove the dangling logic. Any logic that does not drive any output should be removed. And we do it by adding dummy assertion on each of the output. So what we see here on top is assertion written on each of the outputs, and then after running the COI check, we will find all those cover items that don't drive any output, and we can waive them for the next step. And what is this next step? We remove the dummy assertions and left only with the assertions that we wrote. And now we run COI again. And then we will get some out of COI cover items. We concentrate only on the outputs, because if we write an assertion on the output, it will include the internal signals too. and our user just get a list of outputs that are they need to write an assertion on. Therefore, it is a quick and full cleanup, and we got to 100% in all of our designs. But COI is a coarse check, and we need something more robust, and proof core that the tools provide helps us. So just to align on proof core is the actual part of the assertion COI that is needed for proving. Here we have the 3 assertions, and what we see is the cone of them, and the relevant part for proving the assertion. So here only the green part was needed for proving the assertion, and therefore we need to write another assertion that will include the red out of proof core cover items. So we have to find them. We have to write assertions, and not on any on each of the cover items, because we don't want to spend too much time. So our methodology is to first prioritize all those red out of proof core items and take the ones that have the largest fan-in cone. In this example, this point has a cone of 5, and therefore we start by adding an assertion on this location. And it helps us a lot, because if we randomly choose, we might end up with too many places that we want to write an assertion, and writing an assertion on internal signal is not an easy task, so we try to reduce it as much as possible. 2 more things to take care of. One of them is undetermined assertions. We try to run this stage only after the assertions converged. But as you know, it's not always the case. And when you run proof core on undetermined assertions, the size of the proof core may change as you continue with the convergence. So we have some techniques that we won't mention here, but it's something that need to be taken care of. Another thing that we will mention is how we address logic which is unreachable due to gating. So in the next slide, we'll see what does it mean and how do we solve it. So what is the issue here? On this diagram, you can see a signal X, which is reachable, it's green, and it drives only signal Y. And Y equals X and dfx, and dfx is assumed to be 0. So Y is unreachable. So we removed it. We waived it during the stimuli check. But X was reachable, and it's also part of the COI of this output, 01. So it's reachable, part of the COI, but it will not be part of the proof core because it's not really connected. X is not connected to 01 because Y is unreachable. So X is out of proof core, but if we won't do anything to deal with it, we'll say, okay, we need to write an assertion on X and spend our time on that. And we want to save that. As I said, writing an assertion on internal signal can take some time. So what's our methodology? To add a cut point on each unreachable signal, we found that Y is unreachable. Then we add here a cut point and run the COI check. And now X, which drives only Y, is dangling. It does not drive any output, and it will appear as out of COI, and we will waive that. With X and these red 2. Pay attention that these 2 points here, they drive X, but they also drive other signals, so they are not waived. So using this technique, we were able to remove this logic, which is not driving any real output because it is gated. And it's very important to save time on the proof core cleanup. And now we'll move on quickly to the results section. The stimuli violation was got to nearly 0. That's the initial result. That's after cleanup. And we found bugs due to over constraints. And in the checker, we don't see here the koi because koi got to 0 out of koi. On the proof core, we didn't get to 0, but we got to low violation rate. And we found bugs that were found by the new assertions. So in summary, we say that coverage is important in order to take full responsibility of our work, and the tools do a good job, but we need extra work to clean the results. And the flow that we suggested helps us to clean, and during the cleanup find the bugs related to both the stimuli and the proof core. And the bottom line is that coverage is part of our every sign-off, and we are able to get to a good cleanup within a practical time frame. And our future work, we continue to enhance it for different special cases like black box and large designs. And we also started looking on mutation coverage that tools provide and how to clean them. Thank you. And now Emilia will answer your questions.
You're going to answer the questions, Emilia. Okay, thank you very much. There are questions, so we'll go to I'll read some of those out for you. The first question is, I'm not clearly understanding how formal verification could make code coverage completely.
Well, it will not be complete, of course. Formal verification rarely can make anything complete. But with our method, we can try and clean up the relevant parts that we are not going to cover, and then we will have a better measure of how far from completeness we are and what are the steps that we should take to improve our verification.
Okay, thank you. Can we do cone of inference cleanup before stimuli cleanup? Maybe it will save some time in the stimuli cleanup.
Well, we might, but stimuli cleanup is a low-hanging fruit of sorts. So that's the reason we started from it, because we need to have relatively little information about our system, and also it has a side benefit of going over our assumptions and examining them. Having correct assumptions is a crucial part of formal verification, and during the process of assumption examination, we can fix issues with assumptions and get more confidence in the assumptions we have. And it's important to do this cleanup before we are going to proof core, because that's the hard and effort consuming part.
Okay, thank you. A third question is how to check which property belongs to which COI, which COI, please.
Well, there are tools that help us to understand which covers appear in the cone of influence. And it's less important to understand which cover belongs to where. It's more important to understand that it belongs somewhere we care about.
Thank you.
So,
and just quickly, a question for me actually, how much of this is automated or could be automated?
well, a big part of it are automated, and we are using vendor tools, like detection of koi and the proof core parts.
Okay.
So we can we need our knowledge of design when we are talking about proof core, and a
Okay.
little bit less when going about stimuli. But
Okay, thank you very much. That was very helpful.
thank you very much.
No more
Thank you very
questions
much.
came in, so thank you.